probably know because we have David from Edison Design Group. I'm super happy and excited to have David here. Thank you so much for joining us. So yeah, David, as the title says, he's going to talk about reflections on C++ reflections and some efforts that I think he has worked a lot on the C++ standardization process, on adding reflection to the C++ standard. So with that, David, thank you very much for being here, and yeah, please take it away.
Thank you. Thank you. I assume you guys are all graduate students working on compilers. If it's anything like the compiler groups I've been to before, it's mostly back-end work, right? You guys figure out how to do things smarter in optimizations and so on. I, on the other hand, work on the front end. Front ends are easy, except when it's C++. The grammar and the semantics of C++ are kind of arcane. So things are not easy to parse. They're not easy to figure out either. We are a small company. We're 7 of us, and only 3 of us work full-time, really. But we attend most C++ committee meetings to try to understand the language, but we also influence it a little bit. And as Stefanos mentioned, I've been working on reflections for about 7 years now intensely, but I've been working on it that as well. Oh, my slides do go as advanced. But just to be clear, what reflection is, it's the ability of a program to examine itself, right? It might mean that you can examine the whole program, and then you might run into terms like homoiconicity, where the whole program is just data to the program itself, or you might just see a little bit of it, right? So we're not necessarily aiming in C++ at seeing every little bit of your program, because as I said, C++ is arcane, has many idiosyncrasies, and we don't want the library developer to have to become a compiler developer. So we're in a way, we want to present a slightly simpler model of the program to the person who will exploit reflection.
David, sorry, just a small question. I should have asked in the beginning. Do you prefer questions in the middle of the talk, or do you want questions to wait until the end?
No, you can interrupt me at any time.
Okay.
So yeah, I prefer things to be clear, even if we don't necessarily get to the end. That's fine. I've got about 24 slides, but a fair number of them are code, and that takes time to wrestle through.
Okay, nice.
So yeah, so C++ has this mantra that you don't want to pay for what you don't use. And what it really means is that we want to have our features not impose new runtime, like implicit runtime behavior, if we can avoid it, right? So for reflection, we want our reflection to happen at compile time. Whereas in a lot of other languages, it's more natural for reflection just come out of the execution interface, right? You might have an API that while the program executes, you get to look back at its representation. In C++, because the representation is optimized, has no type information left, has no names left, that would not be cheap to add that. Now that doesn't mean that you won't have the ability to do reflection at runtime. It's just that you will then have to explicitly transfer the compile time knowledge to the runtime as a user or as a library. And also, pure reflection is just the ability to inspect your program, but we also want facilities to generate new code from that, right? Like one of the big uses of reflection is things like serialization and deserialization. You would want to be able to generate code that serializes your type automatically, right? And we do have a mechanism for code generation already in C++, which are templates, right? But we're finding that they're not always very convenient to use for those purposes. But we can make do in a pinch. All right. I'll go over a little bit of history. These are just dates that are somewhat meaningful to me. They're not necessarily an exhaustive list, or certainly not an exhaustive list of the important dates for reflection in C++. And I'm not even sure that they are all the most important ones. 1994 was an important year for template metaprogramming. And I'm not sure how familiar you guys are with C++ and with template metaprogramming in C++. but we'll be referring to it once in a while. And so what we discovered in 1994, when this was just a few years after the compiler started seriously implementing templates, was that the deduction process of C++ templates allowed you to do a bit of reflection. Like you could examine types, you could find out whether a type was a pointer, for example, or whether it's class, and take apart a function type. But it's still limited. But you could also synthesize code, and we managed to do some interesting things with that. Now, although that's 1994, it didn't become popular at that time. It was still just a handful of us who were playing with that, and we wouldn't see it become mainstream until some time later. Meanwhile, Shigeru Chiba, who was at the University of Tokyo, but also was working at the Palo Alto Research Center, Park, came up with this system that extended the language. And he called it Open C++, and it provided reflection and metaprogramming as a first-class feature. You can find that paper online. It's still quite relevant. Like a lot of the ideas that were there apply today. Then we get our first standard after almost 20 years of C++ in C+98, and it mostly does not acknowledge reflection. There is a runtime type information system in there, but it doesn't get used very much. And in fact, a lot of shops turn it off because it violates the mantra of don't pay for what you don't get. So if you turn on RTTI, which is usually default in your C+ compiler, it's going to generate object code that you may not like to have in your executable. And then, as I mentioned, in 1994, we figured out that template deduction can be used for reflection, but the first standard doesn't acknowledge that at all. Then in 2003, I had been experimenting with, by then I was working for my current employer, and I had been experimenting with some extensions to make reflective metaprogramming a first-class thing. And I presented that in Oxford at the ACCU meeting. ACCU is the Association of C and C++ Users. And they then asked me to present it to the committee, who asked me to make the slides into a paper. So the link that you see there are the slides of that time. And it also has more or less the framework that we're going to standardize, hopefully, for the next standard, although in a different guise. C+11 was a second standard, and it at least acknowledges some form of reflection in terms of type traits, a type traits header that uses those techniques from 1994 to allow C++ programmers to query types in a standard way and also construct types in a standard way. It's still very, very limited, right? So one of the main things we would like to do with reflection is to look into class types and figure out what the members are. And you can't do that at all in C++11, at least not in a portable way. But the committee doesn't, it's always working. And one of the things that happened with C++11, if you see the number of years between the first standard in 1998 and the second one in 2011, that's 13 years. That was not intentional. We really wanted to have that second standard be done much earlier, but things kind of dragged out. So we changed our approach to standardization to where we said, we're going to publish a standard every 3 years. And whatever is ready and goes. And larger projects will have to straddle multiple standards. And in order to help those larger projects, we're going to create study groups. So SG7 is study group number 7, is the one dedicated to reflection. And later, SG7 was also given the task of studying metaprogramming in general. It started off in 2013 with a proposal that used basically template metaprogramming, but gave it extra power, the kind of power that does allow you to look inside class types. I wasn't really aware of that effort at the time. I was working on modules back then, but in 2017 I did become aware of it, and I didn't like it. If you're familiar with template metaprogramming, it has some unfortunate properties. The first is it doesn't look very much like C++ programming at all. It's its own sort of syntax, if you will. Second is that it's really hard to do because There's no debugging facilities. You get horrible error messages when something goes wrong. And the third is that it takes enormous amount of compiler resources. When you instantiate a template, the front end has to, create kilobytes or megabytes of structures that it never can deallocate until the end of compilation. And so you might be instantiating, say, 100 templates just as a side effect of looking for some information, but those 100 instantiations will stay around, and after a while you just run out of memory. These days, a 32-bit compiler is actually limited because a lot of code just requires more than 4 gigs or 3 gigs, whatever the limit is on your system, on a 32-bit system. So most C++ compilers now are moving to 64-bit models, but still, it's not nice to have a bunch of processes that fill up 4 gigs of memory per process. Anyway, so I came in 2017 to SG7 and I asked to reconsider and to instead of consider reflection based on values, because we can do value-based computation in C++, even at compile time. And those values are ephemeral, meaning that once you do the computation, we can forget about all the intermediate values. We only need the final result. SG7 agreed, and so in 2018, some friends and I published this paper, P1240, Scalable Reflection in C++. And scalable referred to the fact that this version of reflection could handle fairly large problems, unlike the template metaprogramming-based proposal. Still, the two proposals went together for a while, and the TMP-based proposal, template metaprogramming-based proposal, was published as a technical specification. I'll turn on my pen here. And you can find that online as well. You can read it. It does define sort of minimum capabilities that we wanted out of reflection. So it's still a useful process to have gone through. Meanwhile, in order to make P1240 usable, we needed additional capabilities in the language for constant evaluation. And this is interesting. In C++, well, it's interesting to me. The C++ specification does not formally recognize runtime versus compile time. It's a more abstract description than that. But it defines something called constant evaluation, which it is specified in such a way that an implementation could do that at compile time. But it's not required to. An implementation could do everything at runtime if it wanted to. It'd just be a bizarre implementation. All right. Do I have any questions at this point?
David, I have 2 questions. So regarding history, my first question is, are you aware of a compiler that was called Montana? I believe it was in a product called IBM Visual Age, but there were some papers where basically it was back in 1998, and they had a pretty good, it seems, metaprogramming system. But that product and that whole thing never, for some reason, never seemed to become anything big. Are you aware of that? Do you have?
No, I around that time I was good friends with some of the Visual Age people.
Wow.
They had several interesting ideas. I was not aware of Montana. So I'd love to, if you have a link, I'm always interested in seeing what they were doing back then. But it is true that there were, besides the meta object protocol from Chiba, there were a few others, and none of them took off. There are also some today. There's a project called Circle by Sean Baxter, which is a proprietary sort of C++ based language with lots and lots and lots of features for reflection. But it's also not seeming to take off that much. There is another called, I think it's called Meta CPP or CPP Meta. That's out of a group in France. That's a fork from Clang. It just showed up, so we're looking at that. But the truth is, if it doesn't go through the standardization process, I think it's kind of hard to get traction, or to at least have some sort of big corporate backer that will promote the language and make sure that it's used by a large enough community that it's self-sustaining. right? So say NVIDIA, for example, has CUDA, which is a non-standard dialect, if you will, but there's enough corporate backing behind it that it is self-sustaining. But something like Circle or like the Meta Object Protocol, OpenCV+, it's difficult for it to survive in a world where people, they need their tools to live for, to have confidence that their tools will live for decades.
I see. Okay, that's interesting.
But
I
I'd
just
be
posted.
interested. Yeah, if you have a link for Montana, that'd be great to read about.
Yeah, sure. Just posted Montana the paper
On the chat.
on the chat. I believe it may be, you know, and this may be the PhD student in me. It may have something to do with the fact that Montana was published in a relatively unknown conference, so that may have to do with some of the fact that it didn't become very much known. But so regarding your comment on that, if something doesn't go through the standardization process, it generally doesn't get traction. What is your opinion on the like deprogramming language? Because it seems that many of, or some of the ideas that C++, that modern C++ has, like static if and some other reflection features, come from D, like D introduced them earlier, and it seems that some of the main people behind D, so believe Walter Bright and Andrei Alexandrescu, had tried to persuade the C++ Center committee to very early, like late 90s, to adopt some of these features, but for some reason they didn't go through. Do you think that the reason for that is that the community wasn't mature enough yet back then, or maybe the proposals were not as tight as they could have been, or it just wasn't the time, maybe?
So I know Andre pretty well. He's a good friend, and I know I've met Walter a few times. In fact, I think, but I'm not sure that Walter's progress in terms of making functions evaluatable at compile time came out of a discussion that he and I had 20 years ago.
Wow.
But no, I think the reason why it didn't work, and I actually have slides at the end of the talk if we ever get there to that point. The C++ committee is a large beast that requires you to be a bulldog to keep to get proposals through. So if you want something as radical as static if, for example, I think that's doable. But you have to come to the committee not for one meeting, but basically for years and years, reminding people this needs to be done. Don't go with this more reduced version, or if you go with this more reduced version, allow me to come back with an extended version. And you basically have to almost harass the group. It's not quite right. Like, don't quote me on that, but it's you can't just say, well, I'm going to come to one meeting, make a presentation, you'll say hallelujah and bring it into your standard, and I'm out of here, right? It requires it really requires an investment of time and career to get things through. So Andrei Alexandrescu that you mentioned, and who was working a lot on D, is now actually working with me on this proposal. So
Interesting.
he and I have been, like, he now works for NVIDIA, and for the past year and a half, I think, he and I have been discussing. There was a meeting 2 weeks ago in Tokyo where he presented some of his ideas, because he would like things to go much faster, right? Like all of us, we would all like it to be much faster and more capable. But you know, the way the standardization process works, things have to be a bit incremental.
I see. Interesting perspective. Okay, cool. Yeah.
In fact, I mentioned that paper P1240 there. That paper is pretty large and pretty ambitious. And what we had to do to help it get through was take a subset of that. Well, we took a subset and then we enriched the subset with a few things that were not in P1240, just so that it's more digestible to the committee. You know, and we did announce that once we got what we have now through, we will gradually build on top of that and make it richer, and hopefully achieve everything that Andre would like to see in the language.
Cool. Interesting. Okay. Yeah, makes sense.
All right. Any other questions? All right, I'll move on. So from here on out, we'll see some C++ code. It fits on a slide, so it's not huge, but it might be a little obscure. If you have any questions, please do interrupt me and I'll do my best to clarify. All right, so the first slide is just to show the basic mechanisms that we're envisioning for C++. There's a QR code there in the upper right. If you follow the link that's encoded in that QR code, you will land on a compiler explorer page that demonstrates the code on the slide. You should also be able to click on it if that's of interest, and you'll get there also. So it's a hyperlink, and I will do so after I walk you through the code. Let's start with main, right? That's where all our C++ programs begin. And the first thing that we introduced as part of this extension is a prefix caret operator that we call the reflection operator. You can apply it to a type name, you can apply it to a variable, to a function, to a constant expression, to a template, to a whole bunch of stuff that exists in the language as source code constructs. And what that does is it lifts that source code construct into a value of an opaque type. We call this stud meta info. That's the name of the type. But what it represents is a handle into the compiler's internal representation. Right. So by doing it this way, we're not favoring any compiler over another, and we're also not freezing the language definition into a type system. Right. So one of the things that we're often asked is, why don't you have multiple types instead of a single type? So that, you know, I'd have a type for reflections of variable, I'd have a type for reflection of class types, another one for enum types, another for whatever. The problem is that as the language evolves, these notions shift a little bit. For example, a variable in the first standard of C++ was a different set of beasts than a variable in the second standard. And it'd be annoying if we'd have to suddenly change types, because changing types in the standard library is basically impossible because of backward compatibility issues. Changing functions is not that hard. In any case, so this creates a value that represents this enum defined here. And then you can apply a number of meta functions that we provide through this the meta header. In the proposal, it's just called meta, but because this is a experimental implementation, we put in a subdirectory called experimental. So it has dozens of functions in there, and one of them is just to ask for the name of an entity. So this first line will print out my enum as a string. It's a string view, actually, if you're familiar with string views in C++. I can take that same value, right, the reflection of my enum, and I can ask for its enumerators, so the enumerator constants, and then I get a vector that will describe x, y, e, f, and z. So there will be, it's a vector of 5 elements that comes out of it. Since it's a standard vector, just the stud vector type, I can use all the algorithms, all the operations that apply to that at compile time, right? Well, provided those algorithms are valid at compile time. You couldn't like throw exceptions or something at compile time. Although we're working on that. We're working on adding exception support at compile time. In any case, it's a vector, so I can subscript it. I can get element number 1, which, since we start at 0, is y here, right? So now I have a reflection for y, and I can ask its name. So this line will just print out y. I do essentially the same thing here, right? I take a vector of all the elements. I take the number 4, which is z.
Actually, David, do you mind if I ask a question really quick?
No, go ahead.
So for the second line, when you're getting enumerators of, is there a particular reason it's a vector and not, say, an array, where in this case it'd be size 5?
So it is, the problem, it can't be an array because you would have a different type for different invocations, right? But there is only one function, enumerators of. It's not a template.
I see. Got it.
Right. Now, it could be something else. Like we have considered, I don't know if you're familiar with the span type in C++.
Yeah.
But span is more of a view instead of container. And so one possibility would be that you create the enumerators of just once, right? And store them in some static storage in your compiler and then provide a view on them through span. That's certainly possible. We just found that in use, sometimes you really want to have expressions which immediately start adding elements on top of that, and you would not be able, because span needs to be immutable essentially. at least in terms of its number. So we're currently still finding that it's not too onerous to provide a whole vector, and then you can work with it right away and modify it at to your heart's content. But it's a good question. Like certainly there's other options besides to the vector here. And in fact, for name of, we did go with the other options. So the corresponding thing would have been a string. And instead of using a string, we're using a string view there because we don't anticipate that you would necessarily want to change the view in place. It's possible that these things will be revised as it goes through the review process, through the standards process. All right, so this expression here, the last one, the third line that I underlined, provides a reflection value for this element z here. And then I introduced two new tokens, square bracket, colon, square bracket, so the delimiters. And that's sort of the opposite operation from reflection. So instead of lifting a construct into the reflection domain, I do the opposite. I turn a reflection value back into a source construct. So at this point, when this is parsed, the compiler has to know what the value is inside of here. It cannot be it has to be a known constant. It can't be a parameterized constant. I will come back to that issue because it's actually a bit of a strong constraint. In any case, so this is as if I had written z here. Well, almost as if, because no lookup is done. The compiler already has resolved the whole thing. It just immediately replaces like that whole expression by the equivalent representation of z. And so this line should print out 99. All right. Fourth line, it's very similar, but now instead of working on our enum, we're going to work on a class type, right? It's a very simple class type. It's kind of C-like. Yes, go ahead.
Yeah. My question is, why is there like a distinct syntax for the opposite of name of? Like why, as opposed to say like I don't know, as like a function like syntax like name of is.
So say that again.
So name of it has like a function like syntax, right?
It doesn't just have a function like syntax. It is a function.
I guess my question is, why is the reverse also not similar like that, or?
Yes. Because it's so a function has a single return type and can only return values. But when you materialize a reflection as something in the source code, in this particular case, it does provide a value, but it could be a value of all kinds of types, right? In the third line here, it's going to create a value of type enum E. In the fifth line, it's not even going to be a value per se. It's going to be a new kind of expression. It could also produce a type. So it's a grammatical construct. It's not, you can't just represent it as a function. Not in a language like C++, where there's a distinction between grammatical things and value things. You could imagine a language where everything is an expression, and then you don't have that problem.
Oh, thank you.
All right. So back to our fourth line here. So this time I do the same thing as I did on my enumeration, but this time on a struct type. And there's a whole bunch of functions to ask what its members are, but one of them is to only give me the non-static data members. So in this case, there are only non-static data members, so key, flags, and value. I get a vector of 3 elements. I ask for the one number 1, so it's really going to be the flags member here. And I ask for its name, so this is going to output flags. Right. Now, the slides are taken from another presentation I made. And the reason why I chose bit fields here is that in template metaprogramming, bit fields are really hard to handle because you can't refer to bit fields using pointers or using pointer to members. But with our proposal, that's not a problem at all. All right, so it just shows a capability that the previous proposal couldn't handle. And then the last example, hopefully the most interesting one, is I do the same thing again. So I select the flags member. But now I materialize it and I select from an object. So I've got an object S here, which has initialized those 3 fields. and I select the Y member out of it. And this works because, again, we call this splicing, right? The splicer introduces like a source level construct, and it can become anything you want it to become. It can become a type, it can become a namespace, it can become a value. In this case, it becomes a data member reference. It is almost as if you said s.flags, except that there is no lookup that happens, and there's also no access checking that happens. That's a little controversial. There were a lot of discussions on whether reflection should be able to bypass access checking. But in the end, the consensus was that yes, we should be able to do that, but we also want APIs where you're not able to do that. So we can, like in shops that do not want to break the encapsulation, they can exclude the APIs that potentially break the encapsulation. So I'm going to click on this link here, and hopefully this will work for you guys. I don't know how this works in combination with Zoom. So we're landing next. Can you guys see my browser?
Yes.
All right, I'll increase the font size here a little bit. So the code on the left is exactly the code that was on the slide, and on the right here you see the program output is exactly what we expected. So my enum y99 flags. It says 13 here because OXOD is actually the value 13. And if you want to play with this, I encourage you to go on Compiler Explorer. There's more than one implementation. So this is the EDG implementation, but there is also a Clang one. Let's find here, Clang. Here, experimental P296. P296 is our proposal. And so if you use the Clang one, it works as well. All right, I'll close this. Hopefully I can close this. Let's see here. Close this window and go back to my presentation. All right. Well, let's talk a little bit about syntax. As you can imagine, syntax, obviously it matters, right? Syntax is the user interface to our programming languages. When you're in a discussion in the committee, it's amazing what portion of our discussions is what we call backshading syntax. Right, like there's a lot of stuff that's a whole lot more important than the color of the backshed, but that's what we end up discussing and arguing about the most. But ultimately, it's a matter of taste, right? So we've tried various things for this proposal. We're still sort of experimenting with it. Now the prefix operator works very well within standard C++. So far, the caret operator only means exclusive OR. And that's an infix operator, so it doesn't clash at all with its use as a prefix operator. Unfortunately, there are extensions out there, and several of them use the caret operator. The most challenging is Clang. Clang C actually has an extension called blocks, which are a form of lambda expressions. And so it uses the caret as a prefix operator in expression context. It can be disambiguated, but it's going to be a little more complicated for them. We talked to experts of Clang, and they said, yeah, we can do it. We also heard others say, yeah, maybe we can do it, but I don't want to do it. So we'll see how that works out. As it is, C++ is horrible to parse, which is why I'm paid the big bucks. And this is no harder than what C++ already has to do. So we'll probably stick with it. The splicing delimiters elicited strong opinions, both in the committee and if you go on RCPP, for example, on Reddit, like a lot of people think it's super ugly. And I sort of agree, right? It's not beautiful, but you do get used to it after a while. And at the last meeting in Tokyo, I actually tried a suggestion for a different syntax that was more in line with what people had been talking about. And it ran into resistance because people had kind of gotten used to the idea of using delimiters. Part of the problem is that the good delimiters are all overused, right? And in fact, the only really good delimiters are parentheses, because things like square brackets and curly braces are actually difficult to reach on some keyboards, some international keyboards. But they're already overused. We couldn't use those. Once you introduce this idea of two token delimiters like square bracket colon, well, you get a whole new world of possibilities. So we're actually looking at square bracket slash to splice whole declarations in one shot instead of having to splice a type followed by other types and things like that. But that's not part of this proposal. It's stuff that the authors of the proposal are working on. While we were developing reflection, a new paper introduced some new characters in what is called the basic source character set of C++. So as of a couple of years ago, these three characters, arrowbas, $, and backtick, need to be accepted by the preprocessor, and so can be used for token formation. We actually thought about using for the splicer a prefix like we use for the reflection. We would have used $. That's what I mentioned when I attempted to revise the syntax for splicing, and the interest was not that strong. But it's a possibility. So if you ever want to write your own extension for C++, you have some new characters to create your tokens.
But it would look like PHP, right?
Sorry?
It would look like PHP though.
That's true, right? Yeah. And there are already a lot of extensions and pattern languages that use a $sign that way. But you could use ampersand or backtick, there are lots of possibilities. Okay, let's look at another example. This one will illustrate this idea of transferring compile time to runtime. So what I want to do, do I still have my pen? I'm going to write this function in get enum data that's going to create an array this time, right? An array that maps enumerator names to their value, right? So the length of that array is enumerators of e.size because I'm passing the enumerator type as a template argument, right? And that's fairly simple to do with what we've seen so far, right? We just go through the enumerators vector and fill in the array with the name. And then I ask for the value of the reflection. Now, I'm running into this problem again that we've mentioned earlier, which is, in general, this reflection could be anything, right? I do not know, like in the general case, I do not know even if it has a type, because it could be a namespace, it could be a template, right? So value of has to say, in order for the parser to be able to parse through this, has to say what type this expression will be. So value of is a template, and you have to explicitly say what type it is. For an enumerator, there's no problem because all the enumerators have the same type, which is the type of the enumerator. So this works just fine, right? And then we return that array as a result. It's I use auto deduction just for things to fit on a slide, but that works just fine. And then I use the same enum I used before. I can do the members of, print out enum, and I can execute through this. Now, this function was const eval, meaning it has to be evaluated at compile time. But here we're in main. This is actually a runtime loop. So at this point, when I do this invocation, I'm actually transforming my compile time information into runtime information. The compile is making a copy of this array and putting it somewhere in my data segment. And then this loop at runtime will output that array. Have you guys still with me at this point?
I think so. Can I ask a question here?
Always.
So this for loop has a known iteration count and all. So
it does in this case because it's a stud array. We actually know the iteration count, yeah. But it's a range-based for loop. So the way it's implemented in the compiler, it doesn't really know. Like the optimizer will eventually figure it out because it will do constant propagation and figure it out. But the front end doesn't really know the number of loops.
Oh, wait, then I may be missing something because this, like in this case, this is compile time information, right?
It is compile time information, meaning that up to the invocation of this, right, it's compile time information. But the for loop, this is a range-based for loop, is not. It is a runtime loop. So what it's going to do is it parses this, and there's a little protocol for range base where it says, okay, give me the begin and the end of your range as pointer values. And the front end just assumes that those are runtime pointer values. It will not do any attempt to figure, like, yes, they're actually known at compile time, but front end doesn't care. It just assumes their runtime.
I see, yeah.
It just generates an AST as if it were a runtime. If this construct were to appear within a const eval function, then it would add interpretation time, figure it out again. But here, unless you run some heavy duty optimizer, it will not happen at compile time.
I see. Okay, basically
in fact, let's go back to the to Compiler Explorer here, and let me switch to the Clang version. Actually. Hopefully here it is. So it does work on the Clang also, and you see you actually have compile time code here for all the output. I mean runtime code for all the output function. So it did not optimize it. And I think even if I optimize maximally, I don't think it's gonna do much better. Can you guys see the code window here?
Yeah, we can see it fine.
Yeah, we can see it. Yeah.
So it might be a loop. It might unroll the loop, I think. But other than that, it's still all happening at runtime. Like I think it unrolled the loop because the optimizer figured out that this is it's just 5 elements.
So actually, David, I have one question about the value of function
yes.
here.
Yeah.
So I guess I'm just trying to make sure I understand this correctly. So basically, given this std meta info object, and which is here at least, it's a reference to one of the enumerations in the enum.
Right.
And if you give it the enum itself as a template parameter, then value of gives you the value of that particular enumeration in the enum.
That's exactly
right.
A
runtime value.
That's exactly right. And if it were a variable of that type, it would work also. But say you passed it a variable of a different type, then it would fail. So because it's evaluated at compile time, it would stop the evaluation and give you basically a stack trace and tell you why it didn't work. Okay, I can like let's try to see what the Clang version does if I put another type here. Let's put double.
Actually, I was going to ask what the error message looks like.
Here you go. A value of type double can't be used to initialize an entity of type my enum.
I see. Actually, quite readable.
Yeah. And then it says detected during the instantiation. Okay, so this is actually a type error in the instantiation of this. It never got to the point where it evaluated it. So let me try another example. I'll do a value of, I'm going to put a double here of what's the thing? Enumerators off. Sorry, this is live, right? You should never do that during a presentation, I'm told. What happens if I do this?
Is this meant to be outside of main?
Yeah, sorry. That was supposed to be inside the main. Okay, here we go. So call to const eval functions value of with t double did not produce a valid constant expression. And then as a note, it says double is not compatible with the given reflection, which is an entity with type my enum.
I see.
But that's, I mean, it's not fabulous, but it's a whole lot better than what you'd get if you were to start instantiating templates.
I think everyone in this room has been thoroughly abused by that. So to see an error message that fits in this little compiler explorer window is like music to my ears.
Right. We also have as part of our implementation, I think the Clang implementation has it also, but certainly the EDG implementation has a hidden function that you can use to generate output during constant evaluation. So you can do printf debugging basically.
I see.
All right. How much time do we have?
I think it basically depends on when you want to stop. Technically, we have something like 15 minutes.
Okay, there's no way I'll finish in 15 minutes. I have all the time in the world, so it's up to you guys. Well, I have all today for you guys until the early evening, which will be very late for you, Stefanos. Anyway, let's continue. In this slide, there is no yellow and no green because there is no direct use of reflection, but I am using that get enum data function from the previous slide to create a simple enum to string function. And surprisingly, this is the #1 ask from reflection in C++. People want to be able to give at runtime an enumeration value and get back what string that actually, what name, enumerator name that corresponds to. So if you pass y, for example, y has value 1, you get value 1 in here, you go through your array. So I've transferred this to a context variable. You go through it. The first one you enter is 0. The second one is 1. Yes, that's the 1. And you'll return the associated name, which will be y. So this will print out y. This one illustrates a problem which is unavoidable in the C world, C and C+ world, which is f has value 0, just like x. And once you have used x as an expression, f as an expression, its fness is gone, right? There's no distinction between f and x from a language point of view. So this passes in 0. We look through the enums, x is 0. So okay, we print out x. So enum to string f will produce x because it's an ambiguous query, and we, in this particular implementation, we return whichever is the first one.
Wait, sorry. In enums, isn't it the case that like if you initialize a field, then the next field gets the next value and so on?
That's exactly right. And so since e was -1, f becomes 0.
Oh, right. Yeah, right.
So f is 0, and x was 0 also because you didn't specify it, so we start 0. So it's 0, 1, -1, 0, and then 99. Of course,
so would x and f be the same here?
Yes, they're exactly the same. They're exactly
I see.
And that's why
Yeah.
enum to string will return x and not f, because there is no, from a language point of view, there's no distinction. And so our algorithm can, I mean, we could look from backwards and then we'd return f, but we would always return f instead of x then. So I guess moral of the story is don't write code like that. And then if you pass an enumeration value that is valid but does not correspond to any one of these 5 enumerators, you'll get this particular result. Right? You could do all kinds of other things, right? You could create a hash table instead, or instead of returning a string that is just unnamed, you could try to recreate this expression. There's lots of possibilities here. What the reflection proposal offers you is the building blocks to create such functions, and then you make it do whatever you like, right? So we can see this in action. So yeah, y, x, and unnamed. I think you can see it. Let me know if the font is too small.
So I have a question. So does reflection at the moment support only enumerators, or is there like more?
Well, you already saw a little bit of the non-static data members, and we're going. No, it reflects it. So I'll give you a link to the proposal towards the end, and you'll certainly find in the slides. You have the link to the slides. It has a lot of meta functions, so you can examine class types. You can do some code generation. I'll show some examples. We're limited in time here, but if you're interested in this stuff, I definitely encourage you to try the paper. And the paper has examples and links to Compiler Explorer for those examples. All right. So
Okay, yeah.
sorry. Were there any more questions? I don't mean to cut you off. No. All right. So what we really would like to do, and I think Stefanos mentioned the D language, or I think it was you. Some languages allow you to take a string and just inject it, and we would like to do something like that. But it's still a bit in the research stage. There's a lot of concerns regarding security of that kind of behavior, right? Because you suddenly get source code in your program that you may never see. And yet we also wanted that for years. So this proposal doesn't provide string injection or anything like it yet. Although we've done implementations of variations on that idea. But we do provide a few functions that allow you to synthesize code. The first one, reflect value, takes a value that you're computing at compile time and basically adds to the compiler's internal representation, returning a reflection value for it. That's useful to create template argument lists. Substitute allows you to take a template argument list and connect it to a template and get back a reflection for the instance that describes. And define class is a way to define simple classes. At this point, it's mostly C-style structs and unions. And I will show how that works, hopefully in the next few slides. I'm not sure if you guys are how familiar are with the standard library, but the standard library has this type called stud integer sequence. And what stud integer sequence expects is a template argument list that is first an integer type like int or unsigned or long or whatever, and then a sequence of integer values like 1, 5, 7, 42. And it also has this standard library also has an alias, template alias called make integer sequence, which creates an integer sequence with values from 0 to n-1. It turns out that implementing this in standard C++ is quite onerous. It's not hard to do, but when you instantiate it, say for, make integer sequence of 50, it requires so many recursive instantiations that you end up spending a lot of compile time and compiler memory to do that. To the point that most implementations today actually recognize, have an intrinsic to handle this. But with our proposal, you can actually write it as just a function. So here's how it works. I wrote a const-eval function. I create a vector that contains the first argument that I need, so the reflection of type t, right? So that's the t that we have here. We're going to pass it to our reflection, right? I gave it argument n this time as a function, and I just loop and add 0, 1, 2, 3, 4, and so on as a reflection. So reflect value turns this k into an actual template argument in my vector, or a reflection for that template argument. Then I call substitute, and I now have the integer sequence that I want without any kind of intermediate instantiations. Now, this is very technical from an end user programmer. This is, you might not see much of a difference between this implementation and say a standard implementation using a recursive template instantiation. But from a point of view of compile time performance, it's night and day, because this is done very quickly and it doesn't leave byproducts around. It just creates that one integer sequence instance that we want. But also mostly I put this example here to illustrate substitute and reflect value. Do we have any question at this point? I'll still demonstrate it. So what we did is we took the code that you saw in the slide, but I added a static assert that makes sure that the type generated by my implementation here is identical to the type from the standard library. Type from standard library comes from the utility header.
So just a small note here or question. It seems that with this new proposal, you get a lot more understandable code, because in templates you have to do everything with recursion, which I think is more cryptic than this. I'm not was that a goal or kind of a side effect?
It's definitely a goal, and it was one of the arguments I brought to the original proposal, which relied on recursive templates. right? There are languages where recursion is natural, right? Like if you work in Lisp, there's nothing unnatural about working with recursion. But in C++, like you say, you know, our day-to-day programming, it's a lot easier to be able to use loops and just our regular code rather than figuring out how all the angle brackets fit together. And that's just half of the problem. The other half is what we mentioned earlier, is that, you know, instantiation errors are just so hard to debug and to either understand, right? They tend to be very cryptic. All right. And then here, I'm just going to show a little bit of the code. The link goes to the full code, but the standard has a type called tuple, right? Which is what you would think. It takes a variable number of types, and it basically creates a composite type that has members of each of those types, and you access them through get functions. It turns out that implementing tuple is like 1,000 lines of code, because it's hard to create that composite type today. But we have a new meta function called define class that takes an incomplete struct. So a struct that has been declared but not defined, and gives it a definition. And in order to create a definition, you have to give it a list of non-static data member descriptions. NSDM stands for non-static data member. You can give several parameters to the non-static data member description, but the minimum is a type. So and in this case, all I need is a type. I don't care what the member is named. I don't need to give it particular attributes or anything like that. So in this case, I use the minimal version of make an SDM description. I say, okay, I want a list of descriptions for each TS. So the ... here is, I hope you're familiar with pack expansion, but basically it takes this whole expression and repeats it as a list for each argument that will be passed to tuple. And define class then creates a definition for the storage. And now I have a tuple that has a member data that is structured exactly like I need it to be, right? And I can create members like this get ends NSDM that just returns a reflection for the ends member. I'll show you a little more code in the on Compile Explorer here. The standard tuple protocol requires that you have a get member for both the reference case, the const reference case, and the R value reference case. And so it just takes a few lines of code. But you see in about 44 lines of code, I've done what requires hundreds of lines without reflection. And then I have a main that takes this tuple and decomposes it using structured bindings. Structured bindings call into the getter function. So that's why I needed that protocol to work. And the program returns 0, so all those asserts passed. So again, if you have questions, don't hesitate to interrupt me. All right. I'm going to go back again over this issue of syntax versus evaluation. So traditional compile time C++ was just parsing. And so that's a syntactic operation. Then we added templates, and template instantiation is also kind of syntactic, although in our implementation, we literally replay tokens from templates through the parser to instantiate them. But in GCC and Clang, Microsoft does the same as we do, but in GCC and Clang, they copy ASTs and substitute them. But that's still somewhat of a syntactic operation, right? You create a syntax tree. But constant evaluation is different. It is more of it's kind of a virtual machine that runs over your syntax tree. So that's why let's see, do I have in this first example here, n is passed in as a template argument, and that binding operation is a syntactic binding. It allows the n to be propagated as an actual constant value known to the compiler at this point, right? So every instance stamps out a new version of f. And so it's okay to do this. And if I do size of AR, that's a constant known to the compiler. You cannot do that during constant evaluation. So even though f is known to be evaluated at compile time, it is only parsed once, and at parse time, the compiler wants to know what the length of the array is, and n is a parameter. So this is simply not allowed. And you could not compute a constant size if you don't know n. Right? I hope that's sort of intuitive, although it can be surprising sometimes, but it's going to matter in the next example. All right. What I'm going to do in this example is I'm going to take an arbitrary struct, although I'm taking the same one I've always used. And I'm just going to dump its state to standard out. Right. And so ideally, what I would like is to just loop over my non-static data members. Right. And just do like a for loop, and then just do stood out of all of this. Now, the first part is not a problem. Like I could do that and do a name of, and that would work because that's all parsed once. The problem is when I access a member of V, right? V is the member. That access is a syntactic operation. So I can't just use a for loop because it would be different in every iteration of my loop. This would have a different type in every iteration. It would once have an int, but then a double. So this can't possibly be a single expression. I have to stamp out multiple versions of this. So the way I did it is I put it inside a generic lambda. So this thing is a generic lambda where I capture my V value. I give the generic lambda an explicit template argument of reflection type. And then I have in my meta header, I have this expand thing that I wrote. And this is written in terms of the things that we've already seen in terms of reflect value and substitute, right? It takes this whole range, turns it into a template argument list, and then this operator its template stamps out this lambda multiple times for each element of this range here. Right. That's a little bit complex, but once you know the pattern, you just write the pattern. And if you execute that, right, here you go, it prints out key equals 100, flags equal 13, and value equals 42. And you can see how that pattern could be used to serialize your data structures.
So you mentioned that the expand was implemented in terms of other operators we've seen so far. Is that correct?
Yeah. I might even be able to show it to you here. Let me see if I can. Let's see here.
Yeah, I would definitely be curious to see that.
Okay, I think if I do -E here, I'll get the preprocessed output, maybe.
I think it's in the output window, maybe.
Yeah, you're right. Oh, yeah. Let's see. I hope it's not too long because I think it. It's before that. It's before the IS. But I'm going to comment this part out for a sec. So I just have my sorry, I'm not going to do it live here, but I can send you the code. If you send me an email, I'll send you the code. But it's about 20 lines of code. It's about 20 lines of code or so to write that using substitute and reflect value.
Okay, got it. Thank you.
So,
and I know there is a way to find it using the compiler explorer. So if you want to try it, it's possible. Like doing it live is not the most effective. Was there another question?
Yeah, just to briefly return to a previous question. So you could use expand to essentially unroll the loop that we saw earlier, right?
Yeah.
Where I was asking about,
Yeah. And so now there is actually a proposal going to the committee to make this a first class construct. It would be template 4 and then you'd give like something that looks like a range-based for loop, and you give it a body, and it would do it much more elegantly than this. But we haven't implemented that, and it hasn't been standardized yet. And so, but it turns out that you can do it with the reflection features we have. You can actually do it by hand. It's not as pretty, but it works. Okay, I think this is my final example, and I'm not going to show the whole thing, but it uses everything that we've seen so far. And this was written by my friend Barry Revzin. He was inspired by Rust. Rust has the CLAP library, which is command line argument parsing. And what you do, so it's a utility to basically parse the command line arguments that come into your C or C++ programs. And so what you have to do to use it is you just define a struct that derives from this CLAP magic. It's not a magical struct, but it's a struct that uses, it's a class type that uses all of the reflection stuff. And you give it, so in addition to the args type, which is, sorry, the CLAP type, which is special, it also has an option type, which is special. So option says what kind of argument you're trying to receive. It will use the name of the field here as the name of the argument. So if you say an option name, that means that you have either a -- name option or a -n option. The flags here decides if you say use short, then it's going to be just the first letter -n. If you say use long, it's going to use the whole name, and you use -- right? So in this case, we have a name string option, and we have a count option of type int. But if you don't specify it, we want a default value of 1, right? And you just describe your options, your command line options that way, in that type, right? Very declaratively. And then you say args.parse argc.v, and it returns an object that contains the parsed options with, a field called count for your count, and a field called name for your names. Right. Now, this type is different from this type because it actually has a field name of type string and a field count of type int. So the option here is used to encode options. Right. And this is a synthesized type that's made by this CLAP library. And to show you how that works, let's click on this. I passed in -n, so the short version, with compiler meetup at UIUC, -- counts 7, and it outputs 7 times that message. Of course, that's not particularly useful, but if you need to write utilities that have command line options, it becomes trivial to add command line options and parse them. And
this is super cool. So actually, I have one question. So is the function that's doing the interesting reflection stuff, is it this parse method?
Yes.
That my guess is that there's some template magic to basically, once it gets the struct args as a template argument, from there it can do reflection stuff on that to generate the parsing code.
That's exactly right. It uses a feature that you might not be familiar with because it was just added to C++ in C++ 23, which is explicit object parameters. So the constructor of args parse receives as a this pointer. So parse is inside clap, but it receives as a this pointer, not a clap pointer, but an args pointer.
I see.
So if you go to the paper I'm going to reference later, you'll see how it's implemented. It's actually not that much code. Well, actually you can see it here. So here's the clap function. So you get the struct, the options, and here's the thing. See, parse has this weird construct, this spec conspec. So this is an explicit this parameter, which is a relatively recent feature of C++, and it makes use of that. And in fact, my friend Barry, who wrote this code, is the one who brought this feature into the language. So he's very familiar with it. But if you look at, it's not that much code, right? Like we're talking about less than 100 lines of code. Yeah, to implement that.
Yeah, that actually is quite a, that is a lot simpler than I thought it'd be.
Yeah, yeah, it's and you know, it's a yeah, you don't need that much machinery to get fun effects out of this. All right, so the paper is P2996, and you can follow it here. You guys have a link to the paper, so you don't have to necessarily follow this.
It's a small note. So we'll upload the slides after the presentation and the recording.
Okay. I had a few more slides about standardization, but I'm really well over time, so I don't want to consume all of your afternoon or late night in your case, Stefanos.
No, that's fine. You can keep going.
Any more questions? And thank you for inviting me. We're all done.
Stefanos, I think it's kind of up to you if we want to continue.
Yeah, I don't know. Are there any questions on your side?
I don't think so. I think it's actually been, at least speaking for myself, I think I was expecting more stuff to be unclear, but it's actually quite the concepts make sense.
Oh,
Yeah.
good. Yeah, if you like, you know, if you're a C+ programmer, I encourage you to try things out on the Compiler Explorer. It has a lot of bugs. The Clang version has been advancing more thoroughly because it's
Okay.
they have it's done by a Bloomberg engineer who's working on that full time. Whereas for me, it's kind of I work on it every few months. I spend a day on it. But we're making good progress in the committee. It's been very well received, and so the next meeting is St. Louis in late June, and I'm hoping that we might actually get it to the next stage of standardization by then, which would be so the way standard work is it started in SG7 back in November. SG7 passed it on to what's called the Evolution Working Group. They saw it in Tokyo. They'll see it again in St. Louis. And if we're lucky in St. Louis, they'll say, okay, we like this, pass it on to the core review group. And core review doesn't care about design. They just want to make sure the specification is tight and correct. Well, they care about design to the point that they want it to be implementable. So the compiler representatives are in that group.
Okay, that's very cool. So I actually have two questions, kind of more generic, if you're fine with that, David.
Sure.
So one question I would like to ask you is, so why do you think EDG, if you have any opinion on that, or if you can share an opinion on that, why do you think EDG do not follow the open source software model?
So EDG was founded in '88, right? And we started selling a C front end and a Fortran 77 front end, and then Intel. I think it was Intel asked us to do C++, and when we started the company, we thought we would just write front end after front end because front ends are not hard to write, right? And then we would make we'd be sort of a contractual kind of model where we would make money that way. Once we started C++, we realized, oh, this is hard, and it's going to take all of our resources. But we made good money with it because more and more companies wanted to be tool vendors in the C++ space, and so they were willing to give us some good money for that. GCC started around the same time that we started, and quickly went to C++ as well. But then when Clam came around, is when really, as an open source project, C++ became interesting. But we still want to make money, and we don't think we have the resources as a very tiny company to use a open source model as a software as a service. I don't know if that makes sense. Meaning that if you want to make money to open source, you have to sell service instead of source. Right?
Right.
But the source is open, so you can't sell it. You have to serve. Instead, you have to convince people that, hey, our knowledge, our daily work is what you want to buy.
Right.
And to some degree, that's also still what we do, because what our customers pay us is a yearly maintenance fee, right? And they get access to us, and they get to prioritize our work. But we never saw what it would benefit us to make it open source. It also helps for us because some of our customers ask us to do things specifically for them, and they may not necessarily want that to be visible to the world at large. That said, that's a minor thing because although we're not open source, we provide our source for free to research institutions. So a lot of universities around the world have a copy of our front end, and we know for sure that the students that just take it home and keep it for themselves. We're not too worried about the source code leaking, but legally speaking, it's a proprietary source code base, and that just helps us sell it.
Okay, that is interesting. And I guess a second question that is probably related to the first. So EDG seems to be a small team, and yet it produces, it seems, an immense amount of output. And I think, like, what is your opinion on how small teams can work effectively and efficiently? And I think this is, kind of relevant to maybe PhD students, especially people working on compilers, because very big compiler projects actually are created from very small teams of PhD students where, you have 1, 2, 3, 4 maybe, but no, not more than that. So any reflections or thoughts on like how a small team a compiler team can be very productive?
So it's easy start with 2 people, and for the longest time was 3 people. And at this point, it's back to almost 3 because although we're 7, like several of the people who are there are in the 60s and 70s, and they work part-time at this point. One thing that EDG has been very, very productive of is the quality of its source code, and it's not perfect anymore, but we do things like when we do code review, we have a 2-pass code review. There's one review that just checks things for that they make sense, but we actually have a documentation review. So there's someone who makes sure that the format of the code is correct, that the comments are written in good English, every punctuation, every spacing. It makes sure that there is documentation for everything, that the comments are still, what do you call it?
Up to date.
Up to date, exactly. And so that helps us from not descending into chaos, right? It's about 1 million line of codes for us, which is not that much, but it is not that much in part because we've been keeping on refactoring things as we go. Surprisingly, up to a few years ago, this code base was still pure C89. We switched to C++ maybe 5 years ago. And so a lot of the code still has that C flavor, right? But at least now we can instantiate hash tables, which is nice. And the other thing is we have no turnover. Like if someone starts working for EDG, they're very unlikely to want to ever leave the company because it's such a great company to work for. Right. So there's a lot of continuity. Like John, my boss who owns the company, has been around since 1992. So that's 32 years. The founder of the company retired. That's the only reason why he no longer works here is he retired. I got hired out of Hewlett Packard in 1999, so it's been 25 years. Actually, next month's going to be 25 years for me. So yeah, they're just a really great company to work for because we're all friends. We all work from home, and there is one meeting a week that lasts a half an hour, and half of that is just to talk about our weekends. So that, and the money is decent. So that helps a lot, continuity, I think. And then a bit of luck, right? Like we found a niche that has a fairly consistent revenue stream. A lot of our customers, one of the things that we do that gives us value is that a single executable can emulate the Microsoft compiler, the client compiler, and the GCC compiler. If you're a tool vendor, that's something you want. You don't want to have to, create a tool that only works with GCC or only works with client. And then MSVC being closed source, it's kind of hard to emulate all the features. Clang has a Microsoft approximation, but it's not that close. So for tool vendors, it's not that great to try to use Clang to consume Microsoft code, especially because Microsoft doesn't actually parse its templates, which is quite a challenge if your model doesn't work that way.
Okay, yeah, that's pretty cool. Pretty nice reflections. Okay, I think so. Russell, Naren, if we don't have any questions on that side, I think we can almost come to an end.
Yeah, I think. Well, first of all, let's give David a great thank you. This was really quite amazing. Speaking on behalf of everyone here, I really appreciate this. This is quite interesting and very different than the kind of perspective we usually get. I mean, you know, we're at a university. I mean, as you said, actually, I think most of us focus on back-end kind of code generation type stuff. So
yeah.
You were kind of spot on there. So this is a really interesting perspective.
I dropped my email address in the chat. So if you guys have questions that you think of later, or you just anything, you just send me. You're welcome to contact me. Since I don't know your names, do mention that you got it through this discussion.
Sure.
Sounds good. Yeah.
Well,
thank you very much, David. And yeah, sorry, Russell, go ahead.
Oh, thank you. Thank you.
And with that, actually, so Stefanos, I think you can probably stop the recording.
No, I mean, David, thank you very much. This was a very special meetup. Not sure if you realize it, but yeah, it's an honor, I think, to have like people from EDG. I think you're
the honor is mine. I love talking with you guys. I don't know if you know this, but some years ago the committee was in Urbana-Champaign.
Oh wow.
So in fact, were we staying at the college? I don't remember. And my daughter actually got accepted in your PhD program. I don't know if she's going to accept that one, but she has the possibility of coming there.
That's nice.
Congratulations.
Thank you on her behalf, I guess.
Yeah.
Anyway, thank you for inviting me. And like I said, questions definitely welcome anytime.
Thank you very much, David, and have a great rest of your day.
Okay, goodbye.
Take care.